Today, we're going to crack a code that describes literally everything around us, from the fizz in your soda to the stars in the night sky. We are learning the secret language of chemical equations. So let me start by asking you a question. Picture this. You're in the kitchen, baking a delicious cake. Now picture the explosive, fiery launch of a rocket soaring into space. What could those two wildly different things possibly have in common? Believe it or not, the answer is that they're both chemical reactions. And just like any good recipe, whether it's for a simple cake or for complex rocket fuel, they follow a very precise set of instructions. Today, we're going to learn how to read them. So every recipe has a basic structure, right? Let's take a look at the fundamental layout for how reality cooks things up. Okay, this is it, a chemical equation in its simplest form. On the left side, you have the reactants. Just think of these as your ingredients. And on the right, you've got the products. That's the final dish, what you made. That little arrow in the middle, it just means turns into. It's that simple. Ingredients become the final product. Now, before you can read any recipes, you have to know your alphabet. And in chemistry, our alphabet is made up of the elements. But here's the thing, not all letters in this alphabet behave the same way. Some elements are totally happy to exist as single atoms. We call these monoatomic. But others, well, they're the social butterflies of the periodic table. They're diatomic, which means they almost always travel in pairs, bonded together. Understanding this little difference is absolutely crucial for writing things correctly. Okay, now that we know our letters, let's start making some words. In chemistry, we call these chemical formulas. And there are two main types you're going to see all the time. First up, we've got ionic compounds. This is what you get when a metal and a nonmetal get together. You know how they say opposites attract? Well, that's pretty much the whole idea here. So how do we actually write the formula? Let's use sodium sulfate as an example. First step, we just write down the symbols. Na for sodium and SO4 for sulfate. Easy enough. Next, we find their valency, which is just a fancy way of saying their electrical charge, or their combining power. Sodium has a charge of 1, and sulfate has a charge of 2. For the final step, we do this cool little trick called the crisscross. The numbers just switch places and become these little subscript numbers at the bottom. And voila, that gives us our final formula, Na2SO4. Our second type of chemical word is the covalent compound. Now, unlike the ionic ones, these form when two or more nonmetals decide to team up and actually share electrons. And the naming system here is fantastic because it's like a built-in cheat sheet. We use Greek prefixes. Mono for 1, di for 2, tri for 3, you get the idea. So carbon dioxide tells you right there in the name that it's 1 carbon and 2 oxygen atoms, CO2. Phosphorus trichloride, yep, 1 phosphorus, 3 chlorides, PCl3. See? The name gives you the whole formula. We've covered the alphabet and we've covered the words. Now it's time to build full sentences by turning all this into complete chemical equations. We can start with something called a word equation. It's just a plain English sentence describing the reaction. Like we see here, a piece of carbon plus some oxygen gas turns into carbon dioxide. It just tells us what's happening in a really simple way. But you know, chemists are all about efficiency, so we use a symbol equation. It's the exact same story, just told in chemistry's shorthand. Carbon becomes C, oxygen becomes O2, remember it's diatomic, and carbon dioxide becomes CO2. This is the language that chemists actually speak. To make our sentences even more descriptive, we add state symbols. Just think of this like punctuation. A little S for solid, a little L for liquid, G for gas, and AQ for aqueous, which simply means it's dissolved in water. These tiny little letters add a ton of really important information. Okay, we've finally reached the last and honestly the most important rule of chemical grammar. You can't just write whatever you want. Your sentences, your equations, they have to be balanced. This all comes down to a fundamental law of the universe, the law of conservation of mass. What it means is that you can't create or destroy matter. Whatever atoms you start with in your ingredients, you must have the exact same number of atoms in your final product. Everything has to be accounted for. Nothing just vanishes. So here's the crucial point, the bottom line. The number of atoms of each element on the left side of that arrow has to be exactly equal to the number of atoms of that same element on the right side. No exceptions. It's a non-negotiable rule. Let's see this in action. If we react aluminum with oxygen, we get aluminum oxide. But as you can see on the left, that initial equation is all out of whack. It's unbalanced. So how do we fix it? We add what are called coefficients, those big numbers out in front. By putting a 4 in front of the aluminum and a 3 in front of the oxygen, we create a total of 4 aluminum atoms and 6 oxygen atoms on the left. And this perfectly balances the 2 molecules of aluminum oxide on the right, which also have 4 aluminum and 6 oxygen atoms. The scales are now perfectly balanced.
So there you have it, the letters, the words, the sentences, and the grammar of chemistry. You now hold the key to reading the very recipes that build our reality. The only question left is, what will you discover?